Hi, my name is Matt Houghton. I'd like to welcome you to the Andy Sadler Electrical Workshop here at the Worcester College of Technology. Today I will be demonstrating electrical testing. This is the equipment we'll be using to perform the test. We have a mega multifunctional tester. We have a plug-in tester. We have a proving unit. We have a set of safe isolation keys and locks. We have a voltage indicator and a set of test leads complying to GS38, meaning that they have no more than 2 mil showing at the tips. They are fused, they have finger guards, and they have insulation and are robust enough to perform the live testing. This is the board we'll be testing today. As you can see, it's a live board, so the first thing we need to do is safe isolation. Firstly, we need to download the board. And starting off on the right hand side of the fuse board, we work our way across with the circuit breakers, then finally the main switch. The reason why we start at these circuit breakers is that these devices are known as on-load. The main switch should always be switched on an off-load supply. Having downloaded the board, we then insert the locking off device. It simply clicks into the main switch like so. Place the padlock with the warning label. Make sure the padlock's tight. And this, the key, is kept with the person who is conducting the isolation. We can then undo the screws on the fuse board. Like so, and remove the cover. This is the voltage indicator and this is the proving unit. We insert the voltage indicator into the proving unit, and as you see, all the lights display on the voltage indicator. Having removed the fuse board cover, we now place the probe onto the neutral bar and then onto each of the circuit breakers. As you can see, the next circuit breaker along is an RCBO, so we go onto the neutral and the line there, and as you can see, the lights are not lit. We then go back onto the neutral bar there and then onto the final circuit. We then go onto the earth terminal block and do exactly the same. As you can see, the lights are not lit. We then go on to the neutral block, or in this case the RCBO neutral, and then finally onto the neutral block here, and as you can see, none of the lights are lit. We then take our voltage indicator, we go back to our proving unit and retest the voltage indicator. This shows that the voltage indicator wasn't damaged during the test procedure. Having isolated the board, always remember that there are live conductors coming in through the bottom of the fuse board into the main switch. So the rest of the circuits are dead, but remember that these conductors underneath are still live and should be treated with the utmost respect. One of the first tests we're going to do is we're going to check the continuity of the protective bonding conductor, which goes to the gas and the water. So we remove the conductor from the main earth terminal. We then take a test that we've zeroed. We clip it onto the cable itself, give it a little pinch, and then we go on to the pipe work of the water and the gas. As you see, the readings are coming out at 0 ohms, mainly because the circuit is very, very short and there isn't very much resistance in the circuit. Under normal conditions, anything above 0.05 of an ohm, the conductor would actually have to be renewed to a bigger size. Remember to reconnect the protective bonding conductor and make sure the connections are nice and tight. We then move on to the circuits. We'll start off with the cooker supply. So I'm going to disconnect the line conductor, and I'm going to disconnect the CPC. And for this I have a little set of crocodile leads that I can just clip on to connect these together. Again, making sure that they're nice and tightly. We then take the test leads, clip them onto the earth terminal bar in the cooker switch, like so. As you see, we have a little bit of resistance there, and that's showing continuity. If it wasn't showing continuity, it was an open circuit or broken circuit, we would get greater than 999 appear on the tester, like so. We're going to move on to this final one here for the continuity. Simply undo the lighting conductor, a lighting earth cable. Again, place my little clips onto the cables, and unscrew the pendant like so. Clipping onto the earth bar inside like so. And if you look closely enough, you can see that I'm going onto the switch wire side of the circuit. We can then switch the tester on and off. As you can see, that'll go to 999. We can switch the circuit back on. This is actually testing the polarity also on this circuit, because we're switching the tester on and off as we would do the light. As you can see, that's switched off. That switches the circuit back on. We're basically opening and closing the line conductor. This is the ring continuity test. We're now going to disconnect the two line conductors, take them out and split them. We then place our test leads onto the ends of the line conductors. This is now ensuring that the line conductors make a loop through the circuits and it's not broken. As you can see, we are reading 0.00 again. It's because the circuits are very, very small. In a house, you would probably get a lot higher readings. This is also known as the little r1 measurement. We're now going to remove the neutral conductors and again separate them. We then take the test leads and we do exactly the same as we did with the line conductors. Make sure we give the crocodile clips a pinch. And this is ensuring that now that the neutral conductor also is continuous through the circuit. And this is known as the little RN. We then take out the two CPC cables. And again we separate them. And again we put the test leads onto the two ends of the CPC, make sure they're pinched nice and tight. And again this is testing the continuity of the CPC through the circuit. And again, if we didn't have continuity, the meter would read an open circuit like so, as 999. And this is known as a little r2 test. The next part of the test is we're going to place the conductors now into a connector block. If you look hard enough onto the actual conductors, you'll see that they actually have markers on them. This is indicating the longest and the shortest leg. So what we do is we place the longest leg with the shortest neutral. The shortest line with the longest neutral, like so. Like so. As you can see, two longest legs are opposing each other. So what we've actually done now is we've made a continual circle through the installation. And this is also known as the figure of 8 connection. Having connected the line and neutral together, we then go around each of our sockets. Remember to switch them on. And you should get a reading of the equivalent of little r1 plus little rn divided by 4 will give you the readings at each of the sockets. As you can see, this one, the socket switched off, you switch it on, and that brings our tester to close the circuit. All the readings in the ring should be the same, or very close. As this circuit here is a spur, this should be slightly higher because we just have a single cable connecting to it. So we then test that point. It should be slightly higher. Again, we haven't not got a very large sort of circuit here, so our readings are very small. Next thing we do is we remove the two neutral conductors. And we replace them with the CPC. Then go around to each of the sockets, and we, instead of going into the neutral this time, we go into the CPC. We start to get a reading. These readings are going to be slightly higher because we have a smaller conductor offering a higher resistance. We work our way around the ring circuit, and all our readings should be equal. Now, when we did the original test, first test, we had a reading between live and neutral. If I insert this open top plug top, you can see more clearly that on both the tests, this lead has remained on the right-hand side of my plug-in tester. As you can see, on the right-hand side of the plug top is the fuse. On both tests, these conductors here, the two brown conductors, have been used in both tests and given us readings. So we can now establish that the brown cable is the line conductor and is on the correct side of the plug top. We can also establish that during the test that we had a connection in here, which is the blue cable, establishing that is the neutral. And vitally, the top cable has to be the CPC. It can't be anything else. So we've established continuity of CPC, which is R1 plus R2, and also the continuity of the line conductor, which is polarity. Remember, for polarity to actually work, you do actually need to switch the switch on, and that will supply the socket. Next test I'm going to perform is the insulation resistance test. This is to show that none of the circuits are actually interconnected. In other words, the line conductor isn't touching the neutral isn't touching the CPC, and the CPC isn't touching the line conductor. So go to the tester, we set it at 500 volts. We're actually going to pass 500 volts to the circuit, so we do need to be careful of anything plugged in, so we need to remove certain items such as this plug-in tester and this lamp, because this will actually give us readings because they are resistors in themselves. We set the tester to 500 volts. We connect onto the neutral terminal in the fuse board, then onto the circuit breaker, press the test button. As you see, it reads greater than 299 megaohms. Anything less than 1 megaohm, further investigation is required. We then move across onto the line conductor of the ring circuit, and again, as you see, there's no deflection. Then onto the lighting circuit. Remember that we have a two-way circuit, so we need to actually test the two-way lighting as well. We then clip onto the main earth terminal, and we work our way across again onto the line conductors. As you can see, there's no deflection. And again on the lighting circuit, like so. We then go from the neutral to earth, and remember that the RCD also has a separate neutral. Now if there was a fault in the circuit, any of the conductors were actually touching, we would get this sort of reading. As you can see, I've got the two leads actually touching together. So anything that's reading this, there's obviously a dead short in the circuit or an earth fault potential. The next set of tests are live tests and should not be conducted at home unless you are fully qualified. We're now going to measure the external earth loop impedance. So firstly we set the tester from the insulation resistance round to the earth loop. We leave the locking device on the fuse board because we're now going to remove the main earth. If we remove this earth and the circuits were actually energized, then the entire installation would not have any protection. So we remove the main earth like so. We then take our tester, place the crocodile clip onto the earth. Remember to stick the neutral into first, and then finally the line conductor. It does take a bit of time, and we have 0.65 ohms. This value is then compared against the relevant regulations. We can then go on to do the perspective fault current test. Simply move the dial across, and this will give us a value in kiloamps. This is vitally important for if the current is greater than any protective devices installed in the system, they could potentially explode. As you can see, we have 0.37 kA. These are rated at 6 kA, so they are safe. Having reconnected all the cables, ensure that all the conductors are tight, we can now put the fuse board cover back on, like so. We then use a screwdriver to tighten the screws. We then take our key that's been in our pocket all along. We then begin to start to re-energise the circuits. So firstly the main switch. First circuit we're going to test is the cooker circuit. So we energise the cooker circuit first. We're going to do the ZS test on the cooker circuit. So onto the earth terminal, onto the neutral, and then onto the line conductor. And again refer the readings to the latest regulations. The next circuit we're going to energise is the ring final. So we switch on the sockets. Obviously these leads aren't going to be appropriate, so remove our test leads, like so. We then simply insert the plug-in tester. We do this for both the sockets. And we test the spur. Can be a little bit fiddly. And again we compare our readings to the latest regulations. Final circuit we're going to re-energise is the lighting circuit. For this we're going to use a special adapter. You need to unscrew the pendant. Again clip onto the, like so. This is hit and miss. We might get this the right way around, we might not. Luckily we have 0.95. Again you can test the two-way operation of your light switch. You'll also see on the test that we have correct polarity with reference to the installation. Just to prove a point, if I did get the lead round the wrong way, the tester tells you that you've got it the wrong way round. And you simply unscrew it, turn it round, and you're back to testing. And that concludes my earth loop impedance test. The next test is the RCD test. We're going to actually test the RCD of the circuit now on the sockets. So we set the tester to RCD on the half test. We look at the protected device and it actually says 0.03 amps, which is 30 milliamps. So we set the tester to 30 milliamps. We then plug the tester in, and on the half test we press the button. So there's now testing at 15 milliamps, which in theory shouldn't trip the RCD. So then move the tester across to the ×1, and this time when we press the button, and we have 28.9 milliseconds. We reset the RCD. On the top of the tester we have a little button here from 0 to 180. We press that button. That now sets it onto the negative side of the wave cycle. We press the button and we're at 29 0.8 milliseconds. Again, compare those readings to the relevant regulations. We now set it to the ×5 test, so we're going to stick 150 milliamps through it now. Again, we press the test button. As you see, it's tripping at 15.8 milliseconds. Reset it. Again, back to 180 degrees. Press the test button. And we're tripping out at 15.4 milliseconds. And again, compare your readings to the relevant regulations. That concludes the RCD test. The final test we do is the functional test, in which we simply insert the lamps, check that the light's working correctly. I've got a little plug-in tester, and again this just indicates that the sockets are all working. And the final test we do for functional testing is we just press the test button on the RCD to ensure that that works correctly. The next test is the earth electrode test. I've incorporated 2 volunteers here from the college. We've got Eric Brodie and we've got a student, Alex Brodie. Before we go driving any earth electrodes into the ground, we need to check the ground first to see if there's any buried cables, gas pipes, water pipes. So we're going to use the cable avoidance tool. These are the 3 settings we're going to use. There's the power, radio and generation. We're actually going to just use the power for this one. We can also use the radio detection to see if there's any data cables under the ground, but I very much doubt it. First, to actuate the cable avoidance tool is by moving my hand onto the trigger. This makes a beep. I then hold the detector approximately an inch from the ground, and I move in a straight line across the area that I need to check, moving backwards and forwards. This is actually detecting any cables that are running in this direction. To actually see if there's any cables running in that direction, I need to move the detector 90 degrees and do the same process. As you can see, there's no beeps or bleeps at all, so I'm presuming there are no power cables under this lawn. I'm now going to move across to radio to see if there are any other cables underneath. And there are no data cables or pipes under this lawn. This is the tester we'll be using. We've got it set onto the earth electrode test. My colleagues have a yellow and red lead, and I have a green lead. We're now going to stretch these out approximately 30 metres away from the earth electrode. HE. As you see, we have the earth electrode just placed a couple of inches into the ground at the moment, and the cables are run out in a dead straight line. And as you can see on the tester, we have 665 ohms, which isn't really acceptable, but the earth electrode hasn't been hammered into its full capacity yet, so we should expect that reading to come down. You see, we've knocked the earth electrode in approximately 30 centimetres, and the readings are starting to come down now. We're at 462 ohms. Ideally, we want this figure to be less than 200 ohms. getting less and less. We're now in at 70 centimetres, and you can see the value is below the 200 ohms, which we're after. We'll knock the earth electrode as far as we can, and see what readings we can get from this soil. $174. That's the lowest we're going to get. Now, what I'm going to do now is ask Eric to move the second probe 3 meters away, and we're really going to test the soil conditions at that particular point. So Eric, if you'd like to move it 3 meters away from you now. Okay, we're coming out at 175.9 ohms. If you'd like to bring it back now 3 meters, well, 6 meters from where you are now, Eric, back towards me. Okay, it's coming out approximately the same sort of reading. So we know that the resistance of the ground is constant in those 3 particular points. Having taken the average for the 3 readings that we've taken, we now divide that figure by the residual current device, the RCD, that we're going to install. So we had 175 ohms resistance average. We now times that by the 30 milliamps, which will give us a figure of around about 5 volts at the earth electrode. Remember, the touch voltage is 50 volts, so we're well within the touch voltage range. The figure of 1667 does appear in the regs. This will give you an exact figure of 50 volts at the earth electrode. Not that you'd want an earth electrode to be reading 1667 ohms. Less than 200 ohms is considered acceptable. And that concludes the earth electrode test. Okay, this is the cable avoidance tool, the CAT, and this is the Jenny. What we're going to do now is we're going to find a cable that is buried underground. Now, under normal conditions, we would use the power setting and literally trace the ground along until we actually found the cable. But as the light isn't on, we are going to have issues of actually trying to find the cable itself. So what I'm going to do is I'm going to set it up in the generator formation, and we're going to set the Jenny up at the street furniture where the actual fuse board is. This will send a signal into the ground. We'll then trace the signal along the ground to the lamppost and identify where the cable is buried in the ground. So this is the signal generator. We simply switch the signal generator on, turn the volume up, makes a beeping noise. We close the door, and you'll see there's some lines across the top. We simply rest the box up against the street furniture. We set the tester onto the Jenny range, and it should start to beep. Move across, the signal goes. Come back, I'll start to pick up the signal. Starts to fade. You can see it's starting to come along this way here now. Move across. As you can see, the line is coming straight from the street furniture straight to this lamppost. All picked up on the generator setting of the cable avoidance tool. And that concludes my demonstration. Hi, my name is Matthew Houghton and I'd like to welcome you to the electrical workshops. I'll be doing a series of demonstrations. My first demonstration, I will show you how to make an SWA gland and terminate it into an end box. These are the tools I'll be using to perform this demonstration. We have a junior hacksaw, two 20mm spanners, a pair of side cutters, a tape measure, a jacari and an electrician's knife. This is the equipment I'll be using to perform the demonstration. We have a piece of 3-core SWA 2.5 cable. We have an S20 gland kit and a 20mm black enamel terminal box. First thing we do is we mark off the length of cable required for termination. I've chosen 150mm, so I'm going to score the SWA cable at this point. Next thing we do, we use the junior hacksaw and we cut into the SWA until we go through to the metal braiding and we turn at the same time. So as we cut, we turn the SWA cable around. We keep going until we've gone all the way around. The intention is not to go straight through the SWA, but to actually score the metal braidings within the cable. And we should have a score line all the way through the braiding. We now use the jacari to remove the outer PVC from the SWA. Simply pulling the jacari along, this will then remove the outer sheathing, like so. Having removed the outer PVC sheathing, we now remove the steel wire braids by simply waggling the braids, and having scored them correctly, the braids flake away from the rest of the cable, leaving the inner PVC. Having removed the braids now, we need to score the cable at approximately 25mm all the way around to remove again the first part of the PVC. This now exposes the metal braids that have been unscored by the hacksaw. This is the S20 gland kit that we will be using. On the back of the packet we have all the cable sizes with respective gland kits that are required, and for the 2.5 we use the 20S gland kit. The gland kit consists of 2 shrouds, 2 glands, 2 20mm lock nuts and 2 20mm earthing tags. Firstly, we fit the shroud. Using our electrician's knife, we cut through the shroud itself, watching our fingers. This is then slid over the top of my SWA cable and should fit snugly over the PVC. Having taken my gland, I then unscrew the top section, the locking part. This goes over the top of the cable. We then note which way the braids go. In this case it is in a clockwise direction, and by rotating the cable in this direction, this makes it easy to fit the nilled section over the braids. We then we ensure that all the braids are on the nilled section of the gland. Bringing the top section over, we then tighten them up with our fingers and we ensure that all the braids are clamped between the locking nut and the nilled section of the gland. We now use 2 22mm spanners to tighten up the gland. And we ensure that these are as tight as we can possibly get them, as the metal braiding is sometimes used as the CPC in the installation. We now need to remove the secondary layer of PVC by using an electrician's knife, and again it's approximately 25mm across. We need to be very careful this time when we do score this cable so that we don't go through into the main insulators of the cable. So gently does it. As we go along, we can open to ensure that we don't score the main conductors. Simply pull the insulation off, and as you see, the cables are now ready for termination. As you can see from this example, the knife has gone straight through into one of the conductors. We then introduce the gland into the end box or the terminal box. Nip it with our fingers. We then use the 22mm spanner to tighten this into position. We can then either terminate these cables into either a pendant set or a batten holder. We then bring the shroud down, and the shroud sits tightly over not only the gland itself, but also down onto the neck of the end box. As you can see, these conductors or these cables are indicating 3 phases: the brown, black and grey. If we were to use these for single phase installations, we would have to use the sheathing over the respective conductors to indicate that it was single phase. We could then use these accessories onto our end box. These accessories have the standard pin formation that is found on the top of any end box, through box, angle box alike. And to fix these on, we use the 4mm pan head screws. That will be fixed onto there, and final termination will be made inside either of these accessories. And that concludes my SWA demonstration.